Yeah, so thanks again, Firos, for the kind introduction. Thanks everyone for joining and showing up. So yeah, Bangalore microscopy course is often a very big happening. Normally frantic 2 weeks where we have over the day lectures, and then we end up in the catacombs of NCBS to build on the microscopes and to try to find out how optics works. Unfortunately, this is not possible at the moment, but I'm very glad to have this opportunity now virtually to connect to you. So I'll talk a bit in this lecture actually more about TIRF microscopy, I think, than about the interference contrast microscopy techniques, but they're connected, as Firos mentioned. And so I hope I can give you a good overview of how to use these techniques and what we can do with it, even though, of course, I'm sure there's also many other options and many other ways you can use these techniques for. So please, throughout the talk, don't hesitate to ask questions, to interrupt if something is not clear. I'll also have a few sort of break slides in between to sort of address points, and then we'll see how we get through the lecture. So just to give you a rough overview, so I will first talk about TIRF microscopy, what's sort of the motivation for it, what is it used for. As you can see, so we'll talk a little bit what's the kind of physical basis for TIRF, why does it work actually, how it works. And then I think very important, particularly in the aspect of a Bangalore microscopy course, is sort of to show you also a bit the practicals, how to realize it technically when you're at the scope, what are the important elements, what kind of adjustments can you do, how can you maybe avoid some problems. And then we'll go to the interference contrast microscopy techniques. And actually, I will talk about two realizations. So the one will be the reflection interference contrast microscopy, RICM. But then also I will talk a little bit about iSCAT, which is sort of, could maybe say like a follow-up on this technique, which is very powerful to sort of look at even single proteins without using any fluorophores. So this is the first half of the talk, and then after this technical part, we'll have a part about the science, but you know the format. So first of all, now about the technicalities. So TIRF microscopy. So why and what is it? I'm sure you're all now familiar, very well familiar, maybe better than I am, with typical fluorescence microscopy techniques such as epifluorescence microscopy, for example. We are sort of, if you have now like a dummy cell and you express the fluorescent proteins in there, and then you shine the light through the whole cell, and of course you collect then also the signal of the entire protein family that is inside the cell, no matter where it is. So you sort of have very limited information in terms of very limited sectioning powering. Then there are, of course, techniques like confocal microscopy, which are good to sort of slice out a particular section of the cell and just get the signal from that area. But again, if you want to look particularly at surface-related molecules, for example, let's say we want to look at the molecule that is at the membrane of the cell, and that might also be expressed in other parts of the cell, and we only want to see the membrane part, and we want to have a technique that is only exciting fluorophores that are at the surface of the cell. And so TIRF microscopy is such a technique that is that has its power in being very selective for the bottom, for the surface-related proteins. And in the following slides, we will discuss a bit how this comes about, how this is realized, and how we can understand that we can actually limit the signal to only a thin layer of about 150 nanometers to be able to detect and excite fluorophores. And of course, it's not limited to cells. You can use this then for many other questions as well. So just to summarize sort of why or when is TIRF a good option to use, so the total internal reflection fluorescence microscopy. So it's, as I mentioned, it's very selective to the molecules that are close to the surface. It's actually very versatile, so you can, there's no limit of kind of what fluorophores you can use. It can be, there are different ways to realize it. The typical way I do it is via a high NA, high numerical aperture objective. There are also some other strategies for larger fields. You can use prisms, which I can discuss briefly if someone is interested. And then the other nice feature of TIRF microscopy is also that it can be actually combined with other microscopy techniques to realize super resolution microscopy, such as paint or storm, SIM, structural illumination microscopy, and SURF. Yeah, so it's sort of a very, once you have it, you can actually do a lot of different things with this kind of principle of TIRF. And the basics to sort of understand TIRF microscopy and why we actually, how we can generate this kind of thin layer of excitation light, you have a few points that you have to be aware of and that we will discuss. And I just realized I forgot to delete the last slide here, the last line, but it's sort of, so we have the refractive index of your medium is important, and sort of the physical basis of this total internal reflection is Snell's law, and a critical angle is another important feature that you will come across now. So what is the refractive index? I'm sure you have, I mean, I hope you had this in the basic lectures, I guess so. I'm looking over to Feroz, whether he nods, but so any material that is not vacuum, light, the speed of light is reduced, yeah, and this the ratio between the speed of light and the speed of the light in this medium is called the refractive index. Yeah? And here you see, I took this from Wikipedia, sort of a summary of the some of the common materials where we know the refractive index. Yeah, so meaning, for example, if light enters water, then you have sort of a third. The speed is sort of reduced by a third, and the refractive index is 1.33. Another important one that will come up again and again, particularly in microscopy, is the refractive index of glass, of borosilicate glass, which is about 1.52. But I'll have this listed later as well. So, and what happens now with this refracted light? And I'm sure you remember maybe from like simple prism experiments, when your light goes into the prism, then it gets refracted, and actually that angle depends on the refractive index. And so the law that describes this kind of the level of reflection is called Snell's law. And this is here described. And you can see if you have a light that goes in and passes from one medium to the other medium, you see now there will be a difference of speed and of light, and this is related to the difference of refractive indices. And this is also related into the angle of which the light is sort of deflected. Yeah? So if you have this incoming light at theta 1, and we measure it from the normal of this plane, of the interface plane, yeah. So the light comes in theta 1, and then it gets refracted and goes out here at theta 2, yeah. And so the relation between the sinus theta 2 and sinus theta 1 is equal to the ratio of the speed of the light in the medium 2 divided by the speed of light in the medium 1. And this is the same as the inverse, so the refractive index of medium 1 divided by the refractive index of medium 2. Yeah? And this relationship is called Snell's law. So I hope everybody had this. I mean, I think normally you have this sometime in your school career, and then you should see it again sometime in your university career, hopefully. But latest, if you do some microscopy, you should have it there. And if you look at this kind of equation, we can see now well, there are limitations to this law. Yeah, it's not valid all the time. It cannot be fulfilled every time. Yeah, and this angle at which the Snell's law cannot be fulfilled anymore is called critical angle. And to see this, we changed now the equation a little bit. We replaced, if we solve it to see now sinus theta 2, for example, you can see this equation will not be valid every time. Yeah, Because if now n1 is larger than n2, then this factor is larger than 1. And we know that sinus goes from 0 to -1 to +1. So if we reach a theta, an incident angle, where this product is bigger than 1, then this law cannot be fulfilled anymore. Yeah, because the sinus of any angle can never be bigger than 1. And what this means is there's now a critical angle, and we don't get a refraction, we get a reflection. So with an L. Yeah. Is this clear for everyone? I mean, I don't know. If anyone cannot follow, please say yes now, because otherwise it becomes harder. Oops. Later. Sorry for the switch in slides. That wasn't intended. There we go. Yeah. Okay. So I can maybe write this down otherwise, so that you have this. There we have it. Yeah. So critical angle is when so θ1, the critical angle is sort of when we put the critical angle in here, that this factor becomes 1. Yeah. And this is our angle at which total reflection will occur. And just to show you how it would look like, here a little video I took on the microscope. Let me see how I can start the video. I have to take off the laser pointer. So here you see now on the right, sorry, let me first explain it. On the right, I have the drawing. So what I've done here, and you cannot see it properly because it's dark, but there's a glass slide. We come in with an objective where the laser comes through in an angle. And on the glass side, we have a drop of water that is filled with GFP, with the green fluorescent protein. Yeah. And what you will see now is that first I'm below the critical angle. So the laser will go through that drop of water. And that's why you see here now this nice green laser beam. Yeah. Because it's sort of illuminating the GFP on its path. And at some point we will reach the critical angle, and then you'll see what happened. The light beam will vanish. Yeah, that's just to show you sort of how this can look. We move down, and then now we are in the critical angle. Yeah. So it's a very abrupt change from having this kind of light going through, and then suddenly at the critical angle, it's like a very discontinuous change into total reflection. Yeah. Okay. There we go. So, and just to give you an idea, in this kind of setting, so where we have an interface of glass, which has a refractive index of 1.54, and water, where we have a refractive index of 1.33, you can now calculate what is the critical angle. Yeah. And this is sort of how it would look like. So you have to take the inverse of the sinus of that ratio between 1.54, so 1.33 divided by 1.54, and that's about 60 degrees. Yeah. Okay, so this is just to give you an idea. Now we'll see, is this always the same critical angle or not? And in fact, no. So it is important to keep in mind that the refractive index depends also on length of light. Yeah. And again, if you remember maybe from your school experiments, or even, well, if there would have been a microscopy course, or maybe next time you can attend a practical microscopy course, you can see that if you take a white light, for example, you pass it through a prism, you'll see a split up of the different colors, because for each color, sort of the refractive index is a bit different. It's a very small difference, but it counts. Yeah? And here you see a few examples of typical materials, and you see how it changes with the wavelength. Yeah, this is something important to keep in mind, because it tells you also, if you do microscopy with different channels, with different colors, with different laser wavelengths, you have to keep in mind that the angle at which you generate TIRF will change. So you have to adjust for that. Yeah. So this is just to, again, the sort of formal way of writing it, so that now the critical angle is a function of the wavelength of the light. Yeah. Okay. So now we get total reflection. But how can we use it to, I mean, why would we now expect to see anything excited that is above that reflection? Yeah. If the light gets reflected, why should it excite anything inside, so on top of that glass side where the light gets reflected on? And so the reason for that is that when you get a reflection of light, what happens is actually the electromagnetic field, it's not abruptly cut at this interface, but there's an evanescent field that gets generated. Yeah. And that evanescent field has has an intensity that drops exponentially with the depth of the field. And the drop is in such a way so we can sort of define typical or characteristic penetration depth at which we get the signal or the intensity drops by 1/E. And that's normally also used sort of as a good marker that in this area we will excite our flow force. And normally if you can go further above, the intensity of the light will have decreased so much that we don't excite any flow force anymore. Yeah. And so just to give you now a bit the theoretical basics for that, I will not derive how to, I mean, you can do this, but for me, it's now quite a while ago, the last time I did this. But you can sort of derive from if you look at the electromagnetic field and how it interacts with the interface, you can sort of even derive how the field would look like and how the exponential decay is. But that's sort of how the intensity field can be described. So it's a function of the depth, which is Z in our case here. And then you take the initial intensity at Z equals 0. So that's at the interface directly. And then we have the exponential function, which is decreasing with Z and divided by D, which is this characteristic penetration depth. Yeah. And the penetration depth can be also calculated. Again, it depends on the wavelength of the incident laser, and it also depends on the refraction index. Yeah. So that's again, and it depends on the incidence angle. So in fact, for any angle you choose, you will change a little bit your penetration depth. And that's again important sometimes to be aware of that when you're setting up your microscope, that you take care that you're sort of always at the same angle with the same conditions. Otherwise, you might change the depth of penetration, and that will then change again what you can detect. Yeah? How far you can actually detect molecules within a cell or within your sample. Yeah. So this is about the penetration depth. Then we can also ask what happens actually with the intensity values. Just to give you an idea. So the penetration depth, it can range between like 30 nanometers and 300 nanometers. So there you see the value of this kind of surface sensitive technique. We can now sort of limit our optical section far below what is possible with confocal microscopy, for example. Yeah? But of course, with the limitation that we can only do it at the surface, we cannot see anything else in the cell. But at the surface, we are very sensitive and we can slice down to a very narrow area where we detect any molecules. So this is about the light intensity. But I'm sure, as you also know, light is not only an intensity, but light has also a polarization. And so now we can ask what happens actually with the polarization of light, which again, for some applications is important, for others it's maybe less important. But so I hope I managed to draw this in a way that it is understandable. But if you think about now the light polarization, you can always divide your light into two polarization planes. Yeah. One that is parallel to the plane of incidence, and one that is perpendicular. And in this case here, the red curve is describing the so-called S polarization, which is perpendicular to the plane of incidence. And the blue line here, I tried to draw it in a way that it is sort of parallel with this plane. Yeah. So you see the change is sort of within the plane. Yeah. It begins like this. So that's the P plane. And what's important to keep in mind is that the S polarization in the evanescent field, it maintains its polarization. So also the evanescent field S polarization will stay linear. Yeah, there's no other component going in. Whereas in the P polarization plane, we will have an additional component along the longitudinal plane, which makes the which sort of gives now a phase shift to the polarization, and it makes the polarization now elliptical. So it will sort of wheel around the axis and change over time its polarization. I didn't know how to draw that. There are nice Java applets you can find online. I'll have a link later where you can see this, where you can sort of play around with the angle, and you can see how this changes the evanescent field and the polarization. But this is sort of a take-home message, at least. So if you want to maintain the polarization of your beam in the evanescent field, you have to use an S polarization. Yeah, you have to come in with an S polarization. And if you don't really care about it, then it's fine. Be careful if you have P-polarized light that the polarization will be elliptical at the end. Yeah. And if you look at the intensity values, so what happens to the intensity at this evanescent field at the surface, you can have this. Okay, my internet connection is unstable. I just switched off my video. Let's see. I hope you can still hear me. Yeah, okay. So if you look at the intensities of the evanescent field, we see now that, so in the X component, you'll have a bit of a complicated term. And the Y component, let's see again, so you have this 4 times cosine theta divided by 1 minus n squared. So the n is now n2 divided by n1. Yeah. It's just easier to write, so we just said, just make it an n. And so the Z and X component, they're connected. That's why they look also quite similar. The Y component doesn't have any other components, so it stays linear. And the interesting point here now is the intensity values at the surface itself are actually up to 4 times higher than what you get at the intensity of the wavelength of the incident light. So you get sort of a boost of signal at the surface. So that's another perk of TIRF microscopy. That's why it's actually very powerful to look at surface related structures with a much better signal to noise ratio compared to other techniques, because you get not only optical sectioning, so that you don't actually take off the stuff that is above your sample, but also the intensity very close to the surface is sort of boosted up. Yeah? And here again, you see how it changes with the incidence angle. And you can also see that just by changing the angle a little bit, by 10 degrees, you can drop the intensity by like 2-3 times. So you can go from 5 times the incidence intensity down to like 1 time. Yeah, so the angle matters. All right. So these are the, I think the key components that are important to keep in mind when doing TIRF microscopy in terms of the basics. Are there any particular questions?
Yes, sorry. We saw that actually the intensity decreases of the evanescent wave more it moves from the plane of reflection. Yep. Is it possible that the fluorophores also have a decreased fluorescence emission? farther they are from that plane?
So when they get excited, so when the excitation intensity is not strong enough, then they will not get excited. But for the fluorescence, so for the detection, if the fluorophore is further up, yes, you will also detect less because you use a high NA objective. If this is what you were wondering about.
Yes, I think so. So there is a way how the molecules are not excited evenly, I guess. Did I get it correctly?
Yes, exactly. So the whole point is that we don't excite the molecules evenly. So if you think about a stack of molecules, you will only excite the ones that are very close to the surface, and the ones above, they will not get excited. Yeah.
Okay, thank you.
Okay. All right. So, and if you want to read a bit more about that, or just see it maybe in a more coherent manner than me rambling, you can refer here to, so from Olympus and Nikon, they have very nice websites where you can also see these, we sort of have these Java applets where you can sort of play around and change wavelength and change angle, and you get directly see what happens with the TIRF angle. And then one of the pioneers and really very important people who wrote a lot and studied a lot about these these microscopy technologies is Axel wrote. So this is like one chapter that is quite good to read to get an idea about how TIRF works and what it can be used for. All right. So for the next part, I thought I'd go more into the practical parts. So what are the components of a TIRF microscope and how to set it up, more or less. Okay, so this is just a basic kind of technical drawing that I took from a paper. How a TIRF microscope can be realized. So you have first, we use often lasers, so they're very useful, of course. So we have a laser light source. Now in this case, they have a laser combiner. Of course, you want to have different colors as an option. Then the important part is that you have this kind of mirrors from the side, so to steer. Where is it here actually? Okay, this thing is, no, there it is. Okay, so this little arrows, so that means, so that's the important part in the TIRF, so you can sort of move the mirror, and that changes sort of at which angle or at which position the TIRF laser hits the objective. Yeah, because this is sort of how you actually generate the high incidence angle, and in a future slide, you will see this in more detail. But this is sort of one important part, that you have that the laser coupling in is sort of mobile, so that you can move where the laser hits the objective. Then you need, of course, a dichroic. You have a high NA objective that then can generate highly inclined laser beams. That objective is then used also to collect the light that is excited or emitted by the sample. And then I'm sure you're very aware of this. So you have a filter wheel to again select the sort of take away the excitation light. You only detect the emission light, and then you put it on your detectors. In this case, it's a dual color detector, but depends on what you want to do. So this is sort of the basic setup of the microscope. And how does it look in real? So this is now one of the examples. So that's the microscope we have in the lab. It's a Nikon microscope, but it looks very similar, I guess, for other manufacturers. So here the coupling in of the laser is happening at the back, and you have two axes, of course. So you have the X and Y axis. Now in this setting, you have like one axis is controlled by a motorized actuator. In this case, it's the X axis. And here you see the little knob that's for the Y positioning. because what you normally do is you set up the angle in such a way, or the TIRF in such a way, that you only move one of the axes. You rarely move both axes. Yeah? You don't want to mix up your polarizations and your paths. So normally you just choose one plane in which you move the laser around. It's also a safety issue, so you normally don't want to have the laser moving towards you. Yeah. Again, it's difficult to do it online. It would be much nicer to show it in real, but I hope you get the idea. So this is the first part, the laser coupler, sort of, the TIRF module. And what happens then is the laser goes through, and there's a mirror 45 degrees to then direct it towards the filter cube turret. Again, I tried to capture the photo. So this is like the filter cubes. I'm sure you're well aware with these filter cubes. So they contain an excitation filter, a dichroic mirror, and an emission filter on the bottom. Now, the important thing for TIRF is that you're aware to use sort of the appropriate dichroic mirrors, because in TIRF it's very important to have a very clean reflection of the laser light up into the objective, because you come in with quite tight laser beam, and any kind of bending or diffractions there in the dichroic, it can disturb the quality of your field. So what we normally get is like these thicker dichroics. They're sort of, you can find them and you just look for TIRF dichroics. So they're normally thicker glass. There's special care taken so that they have very flat surfaces to guarantee you a very good reflection of the light. So that's one critical element. The next important part is, of course, the objective. So I already mentioned a few times, we need a high numerical aperture objective to realize TIRF microscopy. And this has to do with the fact that you saw the critical angle is around 60 degrees for our typical glass-water interface. And if you put these values in, you can actually find out that, well, that represents a numerical aperture above 1.4. Yeah, so normally you want to have a numerical aperture above 1.4 to be able to generate these high incidence angles. Yeah? With other objectives, you will not generate a high enough angle to get into the critical angle. Yeah. And again, if you normally look for TIRF objectives, you will see they're all like 1.49, 1.45. The other important thing is for TIRF objectives is that you don't want to have, actually this one is maybe not so great, it's a DIC. So you don't want to have any colors in the objective itself, yeah, which can be sometimes inserted for contrast microscopy. Because they would cut away your laser light. Because what happens is you, for TIRF, to generate the high angle, is you come in with the laser at the side, more or less sort of in the side of the objective, where the light gets then refracted quite steeply, so that you generate this high angle, and then you detect the rest. Yeah. Here you see how it looks on my microscope, for example. So this one is 100x, unfortunately, too much reflection. Another important point is for these high NA objectives, you often have then also a correction color. So that's this little element here where you see these little red lines, and there will be also white lines. So they're there that because these very high NA objectives, they're very sensitive also for the environmental properties. So if the temperature changes, for example, from room temperature up to 37 degrees, this is already enough to change a little bit the optical pathways inside these objectives. So there's this correction color to then adjust for the temperature to image it. They also allow you to adjust for the glass thickness to image with. Yeah, because again, we normally use 1.5 borosilicate glass, but some people or some applications you might want to use number 1 glass or thicker glass. And so again, can adjust here in this color for the right glass thickness to then obtain the optimal image quality. Yeah. I don't think I mentioned this explicitly yet, but this TIRF is always also connected to doing then. So these objectives are oil objectives, yeah, because they're high NA. But I'm sure you had this already in previous lectures, what to take care of there when you have an oil objective. Okay, what next? Ah, yeah, exactly. So here are now the points so that I don't forget them. So this is the correction color. One other important thing, again, this might be a bit microscope specific, but particularly if you use, if you want to do TIRF microscopy on microscopes that are also used for other microscopy techniques like DIC also, make sure that there's no Wollaston prism around also. Now, for example, in the Nikon microscopes, these prisms, they can be inserted directly underneath the objective. You don't want to have this there when you want to do TIRF microscopy. Again, this might be different for some other manufacturers, but I just thought it's worth mentioning in case you happen to work with such a microscope. Yep. All right. Then one other important point is to make sure that your laser beam is sort of properly focused and looks proper. Yeah, because again, any impurities in the laser beam, or when they're not properly shaped and there's some speckle of dust somewhere in the pathway, that can really ruin your imaging field. So for this, you normally have either directly after the input of the laser, often there's a little slider where you have a little lens in front, which sort of changes the focusing of your laser. What you have to do, you want to sort of have the laser being focused on the back focal plane of the objective. Yeah? And this is generally, so if you think about the back focal plane, you can also go up to the focal plane, and then you can hold a piece of paper this, and then just see how is my laser shape, how is my laser beam shaped. And if you see it's very diffusive, then you know, okay, it's not really focused, and then you can wiggle a bit, change a little bit the positioning of that little lens, and that will help you then to sharpen the laser beam. And I hope you can appreciate and see that this spot is sort of sharper than that spot. Yeah. To be sure that the laser is actually has a Gaussian beam profile and there's nothing in between, it's also worth, if your microscope room allows, to maybe then even let the laser beam go up on the ceiling and then look at the ceiling, because you get a nice broadened up beam, and then you can really nicely see whether there's any. That's sort of more in terms of troubleshooting. Yeah. Okay, so and of course, so this focusing of the laser spot should be done when your objective is actually already focused on the sample and imaging. Yeah? Because sort of the height of the objective is again changes where your focus point will be. Yeah. So if you so generally what you would do is you would set up already your slide with some water maybe in, or you just put up the objective at the height where you know that your slide will be roughly, and then you can check with the laser and see that it is focused, that it looks fine, and then you can start imaging. Of course, if you have a microscope where nobody else works with it, then you don't have to do it every time, but it's worth, out of experience, I would say it's worth taking these few minutes out to just have a look before starting imaging. Yeah. All right, so that's the laser part, and then you are actually ready to go for imaging. Now, this is just a very boring picture, of course, but how can you actually check how your TIRF field looks like? Now, this is a bit of a biased thing because it's using, so what I think is one of the really good samples to look at the homogeneity of your imaging field is the support limit bilayer. So that's because it generates a flat sheet, and then you can put on that, it will give you a very ideal flat, thin surface. And if you image it and then you see structures in your image, you know it comes from your laser or from your setup. But there are also other ways to check it. But anyway, so just to give you an idea about the limitations of TIRF. So first of all, this one, you see there's this funny freckle here, and you get these spots. So that can happen either when there's somewhere little bubbles still in the path, or, I mean, in this case, we have just a laser fiber where there's, I have to admit, we don't really know exactly where this spot is, but it's part of the microscope. Yeah. So we have to then always be aware that we have to shift it out, or we are limited then to a certain area where we can actually image. Yeah. So the field of view that you can use to properly do TIRF microscopy, if you think about, okay, I want to have an evenly illuminated field, again, it can vary with the quality of your setup and the care with it being set up, but it's also limited just by the physical size of your laser beam and so on. So, and doing like this kind of imaging and then taking a line scan, you can see where do I get actually good signal? Yeah, where do I get a homogeneous or an even field of illumination? And there you can see, okay, you have like an area of maybe 20, 30 micrometers where we get a quite evenly illuminated field. So this is then maybe the spot or that area that I use for any measurements. Yeah, of course, there are ways to then maybe correct for some. I mean, there are ways to sort of correct for these changes of intensity, for the gradients. Then you can expand a bit your field, but you have to be aware of that. So sometimes if you have a camera with a large chip, most likely you will not be able to use the full field of view. Yeah, but there are ways to address that, and there are really great ways to sort of increase now the field of view of TIRF and to make it possible to illuminate much more. And I just want to mention two of them. So one is sort of to use an ND filter in front of the laser, which is sort of neutralizing the Gaussian shape. So it makes sort of a Gaussian beam shape intensity profile to a flat intensity profile, and that will already help you to sort of have a better and more even field of view. I have to say this is not so commonly used, and I think there's only, I think Nikon at some point had this as a commercial version, but I don't know whether anyone else does. And then a more, I mean, a way that I see now more broader used is to rotate the laser beam. So it's can be called ring TIRF or yeah, spinning spot TIRF. And what you do there is instead of having sort of a fixed position of your laser beam, you rotate it now very fast. So several hundred times or so per second, so faster than your imaging. And like this, you generate then an effective field that is that is evened out, yeah, because now you're eliminating the sample from different angles very quickly, and that can generate very large fields of views that are very even. Yeah, it's very nice to get a really big field of view. And then, of course, you have to then get these scalpels, so it's not really cheap to implement. And depends also again on your application. So for example, if you are concerned about the polarization of your light, then you cannot use this kind of approach, yeah, because you will have had now many different orientations of your light coming in, so you don't have any conserved polarization. All right, but just to give you sort of an idea, and of course TIRF microscopy is really widely used, and I think there's many other exciting ways how to use TIRF and combine them with other microscopy techniques to even make them better or tune them to the very specialized kind of detection method. So I'm definitely not claiming this was an exhaustive summary and overview of TIRF, but I hope I could give you a little bit the background of the fundamentals behind TIRF and what to look out for. Just to summarize again, it's a very nice technique to sort of look at surface-specific reactions or surface-specific questions. It's very versatile. I showed you now the way how to do it with an objective. I didn't talk about the prism because I don't have much experience with it, but you can find ways to use a prism to make TIRF. There are also some commercial providers for that. And another feature is the combination with super resolution techniques, but I'm sure again you already had or will have a couple of super resolution talks, so I don't want to get into that. And so before I move now to the reflection contrast microscopy techniques, I want to give one more chance sort of to ask questions or so, or to clarify anything. If there's anything. Okay.
Hi, Darius. 2 questions.
Yes.
So one is, so you are changing the angle to get the total internal reflection, right? So how can you confirm that what you are in the TIRF mode?
Yeah.
For excitation? And second, you said you can have depth of penetration anywhere between 30 to 300 nanometers. How do you calibrate or check what the depth of penetration is?
That are really good points. For the second one, I was just like before the talk started, I thought like, I should have maybe, but I tried to explain it, and I think I can somehow maybe draw something. Anyway, so for the first question, which is about how do I confirm that I'm in TIRF, isn't it? With the angle. So one way is plainly how I showed you in the video. You have to look what happens to your laser. So if I let me just go back. How can I see the other slides? Oops. So the first point is really look at your sample. Here we are. And so you just have to look. So here we are clearly not in TIRF, and here we are in TIRF. So you have to see when do you start being in having the reflection. Yeah. So this is the total reflection. Of course, then you have to look at your sample to make sure that you're not too far. So if you're going too far with the angle, either your laser then doesn't go through the objective anymore, yeah, because you're moving it too far out, then you don't get any signal anymore, or you get just a very suboptimal illumination because you like some super critical angle. Then again, you have to look at your sample and see and play a bit around how is your pattern looking. And that's why it's also important to use something that is, so cells are tricky for that if you use cells as a sample, because often you get a patchy labeling, which is not necessarily homogeneous. So it's hard to make out whether you have some interference pattern in there or not. So whether you have like some dark and brighter spots in your field of view. So either using a slide where you just drop some fluoro on it to absorb it, and then you get somehow a surface that is supposedly homogeneously illuminated, labeled, that you can use, or like a support lipid bilayer that has some fluorophores in there or something like that. But you have to sort of check, and it's always worth to sort of, I say, like play around with the laser angle every time to see whether you can get a nicer field. Another way is to sort of avoid that you, when you don't have an even sample, when your sample is not in such a way that it is even. Another way is to take lots of different fields of use, let's say 100 or so, or 1,000, just do a stream, you move around, and then you take a median of that. And that gives you then normally like how your illumination field looks like, because you get the median of signal from all your different inhomogeneous or heterogeneous fluorescently labeled patches, and that will average out to something more or less homogeneous. So that's the way to go about that. For the penetration depth, yeah, so of course either you So the best way, I think, to sort of calibrate for that is to use something like a bead, even though that can be tricky as well. But sort of the idea is, if you have a surface, let me see, different color, maybe, no, okay. Let's see whether this works. Can I? Yeah, okay. So let's have here the surface, and then use, okay, supposedly this is a circle. So either you use a bead, or you have maybe some, if you get hands on giant vesicles also, that's even better. So something that's fluorescent and round, for example. Then you can, of course, sort of compare how does my epifluorescence look, which should give you this signal of the whole structure. So the important point is now this one, let's say, if it's a 10 micrometer diameter bead, then at half it will be 5 micrometer high. So you want to be really tall compared to the supposed penetration length, depth. Because then what happens is, if you change the color. So if I go in, yeah. So if I come in now and I just have my evanescent field, let's say till here, you get this signal. And then if you go with epi light, everything through, you get that signal. And then you can compare what's that's with, this with, and that with, and then you do some geometry and you get a rough idea whether you get actually a reasonable TIRF field. I have to admit, there can be also problems. So if you use beads, some beads can be a problem that somehow the light that goes in here then also reflects around, and then you get a bit larger halo. But this is sort of the way how you can go about it. And then otherwise, yeah, if you have something like a vesicle, so something that's empty inside and only on the outside some flow for, that would be a much better sample as well. And then I think on the newer like softwares from some commercial partners, they directly even write you sort of what is the estimated penetration depth. But yeah, if you really don't know what your microscope is like and what the powers are, it's definitely worth giving it a try like that to see whether you are in a TIRF. Yeah. Okay. There was one more thing I just remembered. Didn't put a slide about that. But there's something funny in between TIRF and non-TIRF, which is high-low. Just in case, just to have mentioned it. So in high-low, what happens is you're sort of just about to reach the critical angle. And then what you do is you can, I don't know how to come, where's my, is it here? Yeah. So if I go in like this with, no, wait, if I go in like, oh, I cannot draw, sorry. Let me erase that. My hand is not steady enough. So if I go with the lower incidence, then what can happen is that your light gets just refracted, but it's not total reflection yet. Yeah, and you illuminate then sort of again a thin slice of your cell, but it is sort of a little bit inside the cell. So you can get sort of like a micrometer depth or 2 micrometer depths. Again, it's a very special case of application. Some people use it to sort of see structures that are close but not super close at the surface. Just to let you know, again, it's another thing you can use. Sometimes, which can be also a bit a trap, that you're thinking you're in TIRF, but you're actually not really in TIRF because you're in this high-low area. Yeah, so this is called high-low. I should maybe write this somewhere. So if you look for this, you can find more about it. All right. Any other questions? No? Okay. Then let me, I see, oh, okay, I managed already to talk nearly 1 hour. Wow. So this is not too, I mean, this part is anyway shorter, so don't worry. So reflection interference microscopy techniques. So we'll talk about 2 major techniques, and I will really just briefly mention the RICM and then a few slides about interferometric interference scattering microscopy. So RICM is sort of the more classic way. They both rely on the same kind of principle, which is if we have now, again, a surface, a structure that's close to the surface, what we can use then is to look at the interference of the light that gets sort of scattered from that structure, like here, in this case, it's a membrane. Yeah, it has a different refractive index, so there is some reflection going on. And then we can compare we can look at sort of the interference between that light and the light that gets reflected by the glass surface. And if they're, of course, very close, then there's no interference because there's no phase shift between the two and you get maximum intensity. Actually, not the other way around. So if they're just close, you can get destructive interference. If they're in a different distance, the wavelengths, the 2 waves, they might not totally interfere destructively and might add up. So you can get differences in contrast. And this difference in contrast tells you somehow indirectly about the distance difference between your substrate and your object on the substrate. Yeah? So this is sort of, that's why interference contrast, yeah, reflection interference contrast. And again, you see here already, of course, optical properties like the refractive index is important. And in RICM, which is sort of used for decades, it's actually quite straightforward. So this is a typical setup. Nice thing is you don't need, and you need a strong light source. So traditionally, since yeah, it was something like a mercury lamp or a tungsten lamp or so. What you do then is you generate a homogeneous circular illumination, and then you have a polarizer to, again, select now the polarization of your wavelength of your light. You direct it to your specimen. Before that, you put it also through a quarter wave plate. You generate by this circular polarized light. Then it gets reflected. Again, it passes this quarter wave plate. The nice thing now is that after passing, it will be now perpendicular to the incident light. So that helps you then to also sort of select or sort out the incoming light from the reflected light, yeah, by just passing it now in an analyzer. And then you just look at the light intensities, yeah. So these are like the basics of reflection interferometric contrast microscopy. Although it has been there for a long time, it is still very useful. So particularly, again, when you want to look at fluctuations very close to the surface of structures that you don't want to label also. So the other nice feature here of these interferometric contrast microscopy techniques is that you don't need any fluorophore. Yeah, it just works on reflection of the same light that you put in, so you don't have to label anything. It can be very useful. So one example I wanted to show just how it's used is by from our colleague by Bidisha Sinha at iSCAT. That's an application that's actually used quite often to look, for example, at how cells adhere to the surface. And in this question, it was even asked, so how does the membrane of the cell fluctuate on top of the glass surface? And you can see, so again, you have to also decide like at which wavelength you're looking, because this is again a wavelength dependent thing. But it's basically the same kind of setup. You have your arc lamp, you bring in your light, you polarize it, send it in, and then you look at the reflected light, which interfered, where the substrate interfered, so the light reflected from the substrate interferes with the light reflected from your cell. And here you see how it can be calibrated. Again, you do it with the help of like large beads, and then you get these kind of refringent patterns. Yeah, they're showing you the changing kind of patterns of positive and negative interference. And when you do this carefully, you can see here now the calibration with, depending on the height, how your intensity changes. And so you have two informations. The one thing is the major sort of intensity, whether it's positive or negative, and whether it's maximum or minimum. But then also you have sort of the information of total intensity, which tells you whether you're sort of in the first maximum, which is the closest height, and then when you go further away, from the substrate, let's say at like here 600 nanometers, you still get a maximum, but the total intensity is much lower. Yeah. So if you have these two informations, then you can sort of really calibrate your system to adjust or to say, okay, in which range of fluctuations are there. Yeah. And since it doesn't need any labeling, so you can more or less, I would say you can nearly blast in as much light as you want. The other nice thing is you can then record your signal very fast. So you can record very short scale fluctuations. And if you think, for example, about something like membrane fluctuations, they happen at very fast scales. So in this example, they could then look at the membrane fluctuations in the sub-second or second scale, and then map sort of how on a small patch of the cell the membrane height is changing. And you are very sensitive, so you can see, you get the sensitivity of, I mean, like between 0 and 100 nanometers depth, you have a very nice change of signal range, so you can be very precise in terms of how the height is changing in like tens of nanometer range, which is otherwise really not easily to achieve. So these are, and yeah, so for these kind of method questions, RICM is a very good technique and doesn't need much to set up. Yeah, it doesn't need much of fancy equipment also. And one other example, just before we have a break, is I want to talk about is the iSCAT, which is sort of maybe a bit of, I see it a bit as a follow-up on the RICM. It's again an interferometric scattering microscopy. But what they do here now is, instead of coming in with a broad light beam from an arc lamp or so, they use a laser and two AODs, so these are Koester optical devices, which are then used to steer the laser across the field of view. So in a random pattern, they steer the laser around very fast in like a megahertz kind of frequency. And then again, you just look at the interference from the scattered light that comes from your structure, from your molecule of interest, and how it interferes with the substrate. And the collection is sort of the same idea. There's a quarter wave plate between the objective and the beam splitter. So you get again this kind of game of selecting your light by using polarizer and analyzer. And the detector can be a simple CMOS camera. And nice thing here is now, and it's just to show you sort of how is the detector intensity determined. So you have the incident light, of course, and then the important part is there's this phase difference, which then changes this term. And what you do more or less is sort of you take away, these things, they cancel out each other, and then you just look at this last part that is changing a little bit on top of your signal. And that gives you all the information about your structure of interest. So for a small scatterer, the contrast is sort of given by the scattering amount divided by the reflectivity, sort of what comes in as noise, and the phase shift between the two. And again, we don't need any labeling, so you can actually put in a lot of photons. Don't have any photo bleaching or anything like that. Important parameters now to understand the scattering. The scattering is sort of dependent again on the refractive indices of the protein of interest and your molecule, and of course the size of your molecule. And they're both sort of, it all comes together. It is relative and proportional also on the mass of your molecule. Yeah. And that's actually a nice feature, that this scattering technique can be also used to look at, to sort of detect the mass of your proteins or of your objects of interest. And this is also actually used, I think they call it an iSCAT, which is sort of interferometric scattering mass spectroscopy. Yeah. So these are just the basic features to keep in mind, that now the nice thing is to increase the contrast, you just have to put in more photons, which you normally can do. And you can be very sensitive with this technique. So from the lab of Philippe Kokura, for example, with whom I worked a little bit to use this iSCAT microscope, they could go down to like 20 kilodalton sensitivity in terms of how small the molecules can be. So you can actually even detect single actin proteins stuck on the glass side, which is quite amazing. There's also now the future, further developments, of course, to improve the signal to noise ratio. So you can, for example, change your reflector in such a way that it takes out most of the reflected light by just blocking the center part of your light. So you only detect the scattered light that is more on the outside, and that's another way how you can push up the sensitivity of your system. And just one example before we have to break, how it can look like. So if you look, so I'm someone who works a lot with support lipid bilayers. And so of course I take in an example of support lipid bilayer formation. So here what you see is now we have like small unilaminar vesicles, so small liposomes. They're about like 80 nanometers in diameter. And what you do to form a support lipid bilayer is to you drop them on a clean glass slide, and then they will fuse at some point to generate a smooth lipid bilayer. And it was very nice to see this with the iSCAT microscope, because the small vesicles, they're of course small dense entities, and they scatter the light a lot. But once you have formed a smooth bilayer, you will not see much of scattering. So in this movie here, the black dots are sort of the unfused unilaminar vesicles, and then later when you see, where you will see just what happens when they're falling down and reach a certain density, then suddenly you get this whoosh and very homogeneous surface, which is now the full bilayer formed. And again, you can do this without any flow forces. You don't disturb the sample much. So it's actually a very nice way to look at these surface-related interactions. But more to this later in the research talk. And yeah, so any questions?